Hello everybody, I'm Dr. Ross and this is going to be a video about density. I've called it density extra because it's definitely going to be a little bit extra than one might need. It's definitely what one would want, and hopefully it'll teach you something a bit more about density. It ties into the initial density video, the purpose of which was to give my students something other than the power to calculate density, actually discuss what density is and some of its uses, and something other than just in chapter 1 and we never use it again. Okay. Okay, so this is going to involve, it's going to build off of the first video. So if you're watching this first, stop and go back and watch the density video. This is intended to be watched after the first video. Okay, so without further ado, I'm going to go ahead, share my screen. I made some notes. I made them as clear as I possibly can, and I'm going to share them with you now. Okay, so we're going to start off with our continuity equation from the previous video. So take a continuity equation, the one for mass, obviously not any other continuity equation. For local conservation of energy. If you don't know what any of this means, again, stop and go back and look at the other video. I'll state the continuity equation here again. It was the partial of the energy density over the partial of time plus the divergence of the energy flux, and it was equal to 0. Again, all this is explained elsewhere. So take that equation and flesh out the energy flux term. Flesh out the energy flux term. So I should say, so that you don't immediately stop this video and start watching. One of the things we're going to do, by the goal in mind, you'll see in a few minutes, the goal in mind by doing this is we're going to explain why when you spill your coffee or spill any liquid, the volume doesn't change. That's a little anecdotal thing I'm going to explain here based on something that looks a bit more formal. So I'm going to explain, if ever you've spilled your coffee, conservation of coffee, that's what I'm going to explain now. And another thing we'll explain is when you do any gardening and you put your thumb over the end of the hose, the water comes out quicker. We're going to explain that too. So the continuity phenomena. So that's the real world thing we're going to explain with this more formal abstract notation. Okay. So let's flesh out the energy flux term. And remember from the previous video, we said that the energy flux term is going to be energy density multiplied by velocity, field velocity. So we'll say the Q here is the energy density U by a velocity. So again, we've got density in both terms of the continuity equation as an energy itself, an energy density, and as a density, as a flux or a density velocity. Okay. Where U is the energy density. Important because it's a density video. And V is the flow velocity vector field. If you're not sure what a field is, you can go back and look at my video on temperature. Where I believe I talked about scalar fields. I didn't talk about vector fields. So I'll probably have to make another video about vector fields. But essentially, if you look at my temperature video, we introduced temperature as a scalar field or a rank 0 tensor. A velocity field is a rank 1 tensor field, which has 3 degrees of freedom. But I guess I owe you a video on that. Okay. Okay. So we're going to rewrite our equation, our continuity equation, now that we've fleshed out the divergence term, because that's what I want to focus on to explain why your coffee doesn't diverge when you spill it. So the change in U, the partial change in U with time, plus the divergence now, instead of Q, I've said that Q is equal to UV, the energy density and the field velocity. Okay, so we've just fleshed that term out a little bit. Now let's consider the fluid, in this case energy. Anything that flows can be a fluid, so our energy is going to be flowing in a way, so we'll just call it a fluid. So now consider the fluid, in this case the energy. In this case, energy to be incompressible. So something like energy, you know, well, forget energy, think about water. Water is a fluid, it flows from place to place. It can be transported, so it makes sense to look at a continuity equation with water, for example, fluid dynamics. Water, for the most part, and what you would consider classical fluids, like any liquid, a fluid like that, you can't compress it, so we use that fact, the incompressibility of fluids, in earth-moving equipment, hydraulic equipment, for example. It's not true that all fluids are incompressible, but for example, a gas is a fluid. It flows from place to place, but you can compress a gas. But let's consider this energy is not a compressible liquid, or it's incompressible. Okay. So consider in this case the fluid, which is energy, to be incompressible. And this implies that its density is a constant. So if a fluid is incompressible, if it won't diverge or negative diverge, then if you take a slice through it and look at what you have, it's going to have the same consistency. So its density is going to be constant. So this implies, so we stated something and then we look at the implication. This implies its density is a constant. Hence, the density U is 0. Well, since we're saying that U is 0, its density is a constant. Sorry, I didn't mean that. I meant change in density is 0. Obviously, it can't have 0 density, then we'd be talking about nothing. Its change in density is 0. So since du is 0, basically what we're saying is that du by dt is 0, right? Change here means change with time. So essentially they mean the same thing. So du by dt is 0. Now, if the whole thing is 0, then the second term must be 0 as well, which implies that the divergence of u v must be 0. Okay. But more importantly, for what we're considering now, it implies that the divergence of V is 0. Now, we actually stated this a priori, but this is what I'm focused on here. This velocity vector of the energy density, this is what we're interested in here, this velocity vector. Velocity vector. Okay. Okay. So this box term is going to lead us to something that's going to help us explain why your coffee doesn't diverge when you spill it on the floor. So the box term leads to the Gibbs-Liouville theorem. Sometimes called the Liouville theorem, but I like to call it the Gibbs-Liouville theorem because there were two people, Gibbs and Liouville. So for my students, for not my students, the video is all you're going to get. For my students, I'll probably give you some notes from a popular book called Cycles of Time by Roger Penrose about Gibbs-Liouville theorem. Just a little bit, just to give you a bit more than I'm giving you. Why? Because it's going to be useful in chemistry. If it wasn't useful in chemistry, I wouldn't bother. The goal is to make you better chemists. Okay. So the Gibbs-Liouville theorem essentially says the distribution function is constant along any trajectory in phase space. So that's a mouthful. It's really simple. It just has funny words. So I promise you, if you keep watching this video, I'll make it real simple for you. Don't be discouraged by the funny words that people use. The distribution function is constant along any trajectory. I can't write and spell. Can't talk and write, I mean. That was actually proof I can't write and spell. Can't write and talk. Along any trajectory in phase space. Okay, so that is a mouthful. If you see that for the first time, you're thinking, ugh, no way I can understand that. But then you look at it again, and then someone like me will help you a little bit, and then you're like, I'm glad I didn't give in, because that was super easy, and now I know so much more. And now it's starting to make sense. Okay, so let's look at what it says. The distribution, well, I know what that means. The distribution function, let's just say it's a function that's a distribution, and you can almost ignore the word function. The distribution is constant. Well, if something distributes evenly in a constant way, it doesn't diverge. That's all we're saying. The divergence is 0. So del dot V equals 0. We know that's the divergence, the spreading out in space. Formally, the distribution function, the distribution along any trajectory is constant. So it's the same thing. So aren't you glad you didn't stop watching? Speaking of which, I'll try and make this as quick as I can. So just for those that care about the details, a distribution function is just a function with 6 dimensions, 7 dimensions, I'm sorry, couldn't count my own writing. So x, y, and z, so the 3 Cartesian axes, up, down, z, left, right, x, in and out, y. Time, that's a 4th dimension. And then velocity in the 3 Cartesian axes. So velocity in the x, velocity in the y, and then velocity in the z. So 7 pieces of information. position, time, and then velocity in space. Okay. So we're looking at how it moves, its velocity. So where it is, x, y, z, how it moves, velocity, and time component. They're the 7 pieces. All right. So now I want to introduce what phase space is to you. I want to explain what phase space is, because if you've never heard it before, you might wonder what it is. It's got nothing to do with phases like solid, liquid, gas. It's just a 6-dimensional space that Newtonian mechanics is written in. So if you've taken any physics, you'll know what phase space is. If you haven't, you probably just turn the video off, and hopefully now you've just come back and we can learn what it is together. So let particles of a fluid, because we're talking about a fluid that's flowing, let particles of a fluid be points in a 6-dimensional phase space. Let particles in a fluid be point particles or points in a 6-dimensional phase space. That flows with time. So that's our 7th dimension. So the 6 dimensions plus 1 dimension of time is the 7. That's what we said the distribution function was. Hence forming trajectories in 6-dimensional phase space. So phase space essentially is position momentum space. So phase space, this funny term here, it just means position momentum space. Space is just a collection. Here it's a collection of positions and momentum. Let's call position for now, at least let's call it X. Let's call momentum P. Now, remember we've got X. Really, I shouldn't have called it X. In fact, let's just call it, no, let's call it X. I'll call it X in my notes. Typically it's called Q, but I don't want to call it Q because I used Q in my earlier density video. The problem is all these symbols are used for multiple things, and it's okay using the same symbol in different videos, but in the same topic, to use Q more than once is awkward to say the least. But why can we have 3 X's? Well, we can have, X just means position, so I can have position in the X, Y, and Z direction. I can have 3 momentums, momentum in the X, momentum in the Y, momentum in the Z, and then time, that's my 7. Okay. So I can have trajectories. Now trajectories in phase space, position X, momentum P, so position X and momentum P, so here's our graph here of phase space. These trajectories with time are energies. So let's call it energy 1, let's call it energy 2. So again, to add weight to our idea of continuity equations or conservation equations, notice these lines don't intersect. That's how they stay conserved. So these trajectories that stay independent in phase space, that's another way to express conservation of energy. And I'll come back to this when we look at energy in a later topic, but it does relate to our previous density video on continuity equations. Okay, so we've said that X is position. We've said that P is momentum. So that's our phase space. Okay. We've also commented why it's 6-dimensional. So why 6-dimensional? Well, it's 6-dimensional because of you've got position X, Y, and Z, and then you've got momentum X, Y, and Z. So that's why it's 6-dimensional in that 7th unit of time. Okay, so we've introduced something new. We're learning something new, phase space. Okay, so imagine an ensemble. An ensemble is just a word for collection. An ensemble of a large number of particles in this phase space, because we're going to look at the density of it now. An ensemble of a large number of particles in 6-dimensional phase space. Good thing about me actually writing this when I speak is that I can do it slow enough that you can actually write it when you watch. Because sometimes you watch videos and the professor's going blah, 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 and you're like, what? But at least I'm doing it slow enough because I'm writing it down that you can actually write it down too. And hopefully my students are writing this down. So an ensemble of a large number of particles in 6-dimensional phase space can be described as a density. Can be described as a density, because this is a density video. We're going to call this density rho. You typically call density of a fluid rho, RHO. And this is density that is in phase space, so it's a function of position x and momentum p. Rho density, x position, p momentum. Okay, we are ready. We are locked and loaded, ready to look at Gibbs-Liouville theorem now, which will tell us why our coffee doesn't diverge. So here we go. Gibbs-Liouville theorem says that the change in the density of our phase space, which is a function of position and momentum, per unit time equals 0. That's what Gibbs-Liouville theorem says. And it also says that the divergence of our density, which remember is a function of position and momentum, is 0. Okay, so it's a direct extension of our continuity equation. As you will recall, when we recall our continuity equation. So recall, if we put back into our continuity equation, put back into our continuity equation. Remember, a continuity equation can be applied to anything that transports, any object that transports a real object, not an abstract object. So we can write our continuity equation where we've got change in density per unit time. We've got our partial derivatives plus the divergence of our density as a function of position and momentum. And then remember, if I put density here instead of flux, I've got to put density velocity. Okay, so I've got density in both spots, the time density, the space density consideration, and velocity. Okay. Okay, so we're doing quite well. We're about halfway through this video. I'll try and go as quick as I can. The last half should be quicker because the abstract stuff is up front and then the more mundane stuff is later on. So if you don't like math, fast forward the video right now. If you are a chem major or a science major, you probably want to look at this, possibly not stress too much about it, but it's definitely something if you watch it 2 minutes later, you'll get it. I want to include it anyway. A proof of the Gibbs-Liouville theorem. This will make it all the more sweet when we turn our attention to our coffee fluid in regular coordinate space. So proof of the Gibbs-Liouville theorem. So let the divergence of our fluid density in phase space be written. Oh, actually, I should. I just want to comment because I've just realized I didn't comment on it. Remember, we said we're going to assume here that this liquid is incompressible. We're going to assume that this liquid is incompressible, so keep that in mind. Okay, so let this be written as in fact, I don't want that, do I? I want, no, I do want that. I'm sorry. I do want that. Okay. So let this be, instead of X, typically if you were to Google this, for example, you typically have position as Q, just so you can say Q in the X, Y, and Z direction, rather than X in the X, Y, and Z direction. So Q and P, where Q just means position. So position. And P is momentum. So all I've done, I've just relabeled X with Q. Then the divergence of this thing, rho Q P, rho that's a function of Q and P. So here's the statement. It's not that pretty, but it is that simple once it's explained. It's the sum over all I, the partial position dot I, I'll have to explain what dot is in a second, but give me a second, over the partial of Qi without the dot. So one Qi, the numerator has a dot over it, the denominator doesn't, plus the partial of the momentum I dot over the partial of the momentum, and that's equal to 0. So this is it in all its ugly detail, but I promise you it'll be straightforward once we have a little talk about it. Okay, so let's just pause for a second and we'll say what some of these things are, and you realize there's no big deal. First of all, these dots. So let Q dot equal dq by dt. And let momentum dot equal d momentum by dt. So the dot is just Newton's abbreviation for expressing a time derivative. So how does position change with time? You can either write dq by dt or you can write q dot. How does momentum change with time? You can either write dp by dt or p dot. And hopefully you'll agree that just writing a dot is a time saver. Okay, now we're gonna have to look at how we can relate Q and Q dot and P dot. There's some background here, I'm not gonna go into it. Anyone that's taken physics will recognize these as Hamilton's formalisms. But if you haven't, don't even worry about it. I'm just gonna state them and we're just gonna plug them in. So let Q of I dot equal the partial change in energy over the partial change in momentum. So I've got an equation with a P and a Q dot in it. Don't really, if you look at the units here, you can figure it out. I've got energy over momentum is velocity, of essentially position dot, or the derivative position is velocity. So if you look at units here, velocity has the same units as energy over momentum. And let P dot which is the time derivative of momentum, equal minus the partial change in energy over the partial change in QI. So these are Hamilton's formulas. Almost I've ignored something and just put energy in, but it doesn't matter for us. But essentially I've got something with P and Q dot in it, and I've got something with Q and P dot in it, and that's all we need. So let's sub in the Q dot back into our Gibbs-Liouville formula up here. So I'm going to take these Q dots and I'm going to sub them in here, and then take the P dot and sub it in here. That's what we're going to do. Okay. So pretty straightforward. It implies that the divergence of our field, which is a function of position and momentum, is the sum over all points. So everywhere in phase space there's a point. Let's call generically them I, and we'll sum over all points I. So we're really summing over a field. Well, if I look at what I had the partial over the partial of Qi, and then I had the numerator was Q dot. Well, Q dot is just the partial of energy over the partial of P, right? So I've just substituted in, instead of writing Q dot as the numerator, I put partial delta E over partial delta P plus, but that plus is going to be relegated to a minus because I'm going to add a negative quantity for P dot. So it's going to sum to a minus sign overall. And then I've got partial over partial P at all positions I, multiplied by the partial energy over positions Qi. Now, in partial derivative land, and for the proof of this, you'll have to see my partial derivative video, which won't be in this video, mercifully said. If you look at this sequence here, it's reversed, but fortunately, for reasons that will be explained later on, the order doesn't matter. This is not true of regular derivatives, but if you see a partial sign, you can exchange the order for reasons that will become clear in another video. So then they become identical statements. So this term is the same as that term, provided the order doesn't matter. So that's why it sums to 0. So we've proven a statement that we made earlier on. We made, well, where did we make the statement first? Yeah, we made it right here, right? We stated it, now we've confirmed why. Okay, so it truly does sum to 0. All right, so now what? Now we know everything we need to know. You know, you can look at that a few times, but now we're ready to explain the most important thing, why when you spill your coffee, it doesn't diverge, which, let's face it, that's the most important thing in this video. So let's put this in words. Incompressible fluids don't diverge. I said diverge, but I was supposed to write don't. And my brain unitasked away. Don't diverge. That's why they're incompressible, right? They're incompressible in either direction. Here's our everyday example. An everyday example number 1, because I'm going to give you 2 everyday examples to really make this stick out in your mind. First one is my favorite because I like coffee. Maybe you do too. This diagram will make everything make sense. The reason why I didn't put this diagram at the start of the video, nobody would watch any of the video after seeing this. So hopefully this is the treat after the medicine or what have you. Okay, so let's say there is a small cup of coffee. And maybe nobody's here watching this late in the video, who knows? But hopefully we'll see. There's coffee in a cup. And over time, worst case scenario happens. You spill your coffee. And all of the delicious, yummy coffee is on the floor, spilled all over the place. Okay, so that's the very easily to understand scenario. So you've got coffee out of the cup. Okay, coffee in a cup, come back a bit later, coffee out the cup. Oh no. What we're saying is if coffee essentially is water, it's an incompressible fluid, it won't diverge. It won't change volume. So we're stating that the volume of coffee initially is equal to the volume of coffee finally. That's all we're saying. That's all we're saying. If it were any different, the divergence would not be zero. So that's practically what I would remember. And that's the mathematical formalism. Just that explains it. It just explains it. Okay, so that's practical example number one. Here's my last page and practical example number two. Yes. So here is my final page, my everyday example 2. Okay, so imagine you have some kind of garden hose. You get a lot of mileage out of considering garden hoses. So it's got a thick part and then it tapers off to a thin part. I'm just looking at this section here. It carries on that way. It carries on that way. And I'm just looking at this slice here, or this bit in the middle. Let's make this a bit longer. For reasons that will become clear in a second. Okay, let's say we're looking at this thick part. Which goes from here. It's not exactly uniform. Maybe I could have made it uniform, but I tried to make it a little bit realistic. So let's say there's definitely this part that's different than everything else. Okay. So let's call this A. Not for area, just region A. And we're going to have the skinny part's going to be region B that we'll see in a second. So right now I'm only considering region A. Okay, region A. And region A has a length where the length of region A is the velocity of the fluid traveling in region A by the time it takes for the fluid to traverse the length. So length is speed times distance. That's a common equation that you learn in grade school. And here we're just saying it's because we're measuring the length of the tube by the velocity of the liquid that's flowing continuously through the tube. Okay, so now let me write some words so this diagram hopefully makes sense. So take a fixed volume of water in a large section A of a pipe or a garden hose pipe. Take a fixed volume of water in a larger section A of a pipe. Now consider what happens when the same fixed volume of water enters a small region B of the same pipe. Now imagine what happens when the same volume, same fixed volume of water enters a small section B of the pipe. So I'm going to redraw the pipe, label it B. So we'll have two diagrams. It'd be nice if I could see the first diagram so I can get the scale right. Okay. Do my best to get that scale right. Not doing the best job in the world. Okay. Okay, so we're going to consider section B. Never understand why they put buttons on a stylus pen. That if you press them, they do something you don't want them to do. But you have to put your fingers right where the buttons are. Anyway, I digress. Okay, so we'll shade in, so all of that volume, that shaded volume, it can't go anywhere. It's incompressible, it's an incompressible fluid. So it has to go in the pipe somewhere. So we're in section B now. And this length B is going to be the velocity of the water in B times by the time it takes to traverse B. Okay. Okay, so that's the setup. But since the water is an incompressible fluid, the volume can't change once it enters section B. Thus, the length of the pipe must increase. The length of pipe housing the volume must increase. Okay, so I'll pause for a second. Hopefully that's straightforward. If we look at the two, if I can scale this maybe a wee bit. Ah, there you go. So if we look at the two diagrams side by side, as the fixed volume from A, it's an incompressible fluid. So that means it can't be compressed that way in the positive direction or that way in the negative direction. Or it can't diverge in the positive direction or diverge in the negative direction. It has to be accounted for. Constant volume, just like our constant volume in our coffee cup, right? Constant volume. So it has to occupy a longer length of pipe. So that's the key to the insight right there. It has to occupy a longer volume of pipe. Well, if it occupies a longer volume of pipe, let's look at what the length is proportional to. So since length of pipe, the longer length, LB, is equal to VB dt, then the velocity, if we cross multiply for the velocity is length B over dt. So the velocity is proportional to the length. We already said the length is longer. The velocity is proportional to the length, so the velocity must be greater. So a greater length of the pipe in the smaller section means a greater velocity. So thus, water travels faster through a narrow pipe. Water travels faster as the pipe narrows. And we've all done it. We've all hosed the garden. You put your thumb over the end, you narrow the entrance or the exit, and then the water seems to come out faster so you can make a stream. So I'll just comment for the record, think what happens when you place your thumb over the end of a garden hose. Think what happens when you place your thumb over the end of a garden hose. Okay, so that concludes this video. So this was a toughie. This is not for everyone, but hopefully it's for everyone. You know, I'd be thrilled if all of my students at least have an appreciation for what was mentioned. This is the second density. I plan on it being the last density video. So we hit density right at the beginning of the course, and you learn how to calculate it, and that's it. So I've supplemented with these two density videos. The first one was linking it to continuity equations, which is going to come up in conservation of energy. And this one is linking it to ultimately Gibbs-Liouville theorem, which will actually help you, just for a heads up, it will help you in the second sequence of general chemistry when you start looking at entropy and things like that. If you have a feel for Gibbs-Liouville theorem already before you start looking at entropy, you'll be all the better for it. So just to summarize, we started off pretty abstract. We acknowledged it was extra. We rephrased our continuity equation from the first video, and then we started to dig in a bit more. Okay, what do you mean by energy? What do you mean by density? What do you mean by the flux of the density? And then we stumbled into something called the Gibbs-Liouville theorem. We learned a brand new space called phase space, which will help you in physics class, no doubt, and in art class too, but certainly in physics class. And then finally, we linked it to something that's very straightforward. We linked it to something as mundane as spilling coffee or getting the water to come out faster from a garden hose by putting your thumb over the end. So hopefully pretty concrete by the end.